Forget it.
Hello, and welcome to this episode of Physics for Show, when we talk about stagecraft, physics in theater. Today we're going to talk about moving scenic pieces on dollies, when you have to put something on wheels to move it from one place to another. We do this a lot in theater, as often we're building in a shop and we have to move the scenic pieces onto the stage. We do that using dollies. A traditional dolly you may be familiar with moving appliances looks like this. It's got two wheels, a lip on the front, and handles. That's one way we can move some scenic elements, furniture, dressers, things like that. Another dolly can be plastic and square, have four wheels, and you put it on the ground, it rolls around. Got one here, made of wood. Woo! Can feel like a skateboard. Now you might be asking yourself, how much weight can a dolly hold? If you buy a dolly from the store, it will definitely give you a weight rating, and you can load as much as the weight rating says, as long as you're using it correctly. A handmade dolly, such as this one, you would have to use your own structural engineering to come up with the weight rating for yourself. But that's okay. That's just a few math equations away. Two by four and 1x4. The difference between this is a 2x4 is twice as thick than the 1x4. You just kind of see here, 2x4, 1x4. The ratings of a 2x4 and 1x4 can be found online, an easy Google search. The type of wood you're going to look for is called SPF. No, it's not sunblock. It's a type of wood that stands for spruce, pine, fir. Now that I've introduced you to the 2x4 and the 1x4, we're going to go into what their actual dimensions are. The names 2x4 and 1x4 are actually the nominal dimensions. Our actual dimensions have to be measured with a tape measure. Now the 2x4 actually measures at 1.5 by 3.5 inches. But if we were to call it a 1.5 by a 3.5, hey, pass me the 1.5 by 3.5. It's a mouthful. We call it a 2x4. As for the 1x4, we measure its actual dimensions, and we get about 3/4 of an inch by 3.5 inches. 3/4 of an inch by 3.5 inches. You can definitely find information about this in books. For instance, this is the Backstage Handbook, and on page 24, it illustrates the kind of dollies used backstage. So I'm going to do my best at drawing, but just remember this is what it looks like three-dimensionally. We're going to do a picture of it, a side view, two side views of the dolly. First view of the dolly looks something like this. To which you can also see its casters. That's my best drawing of the dolly. The other view of the dolly looks like this. This. So these two side views of the dolly indicate the way that the wood is crossed and that the casters lie under the thickest points where the wood is crossed. Now when you're loading a dolly, you really want to load a dolly so that the force that you're imposing on it goes there, down onto the casters. That is where the dolly is the strongest. Again, these are our side view. Now, we'll draw a little bit of a bigger dolly so I can show you how a dolly can be loaded incorrectly. first setup. Now, if you load your scenic elements such that all of the force is coming down onto this piece of wood, it is not being distributed properly all the way out to those casters. What it's going to do is it's going to cause a bending moment here in the dolly. You can see here in this drawing how the combination of the forces is creating a bending moment right here at the weakest part of the wood. So where the load should be translating down through the casters, instead it is transferring directly into the weakest point of the wood. Now that we're talking about the bending moment, I'd like to show you the difference with the 2x4 and the 1x4. The bending moment equation is M equals 1/2 force times length. The length of the wood, the force being applied to it, and 1/2 of that length. So it's assuming that center of mass. That is what we've got for a bending moment. So let's fill in what we know. Well, we do not know the force yet, but we do know our length. And when I measure the dolly, I end up with a length of 18 inches. There's another equation I'd like to bring into the picture, and that's where the beam will fail. We talk about breaking beyond the bending moment, the actual breaking moment, and the beam will fail when the max stress applied equals the ultimate strength of the wood. So let me put that into an equation. The max stress equals the ultimate strength. So we get the bending moment times the height of the wood, which is another given we have, all over 2I, the inertia, equals the ultimate strength, which we'll give that, we'll give it a capital U for now. And that is going to be in pounds per square inch. So what we do know, we know the length is 18 inches. We can also break down the unit, the 1x4, into a picture something like this. Let's say it goes off. There. So we remember this length here was 3/4 of an inch. And this length here was 3.5 inches. So we're going to take those two things into consideration. So our H for this equation is equal to 3/4 of an inch. Also, it's kind of easier when you're working with a calculator to put things into decimals. So we're going to call that 0.75 inches. What else do we also know? Well, I, the inertia, is a whole separate equation. The moment of inertia has its own equation. Let me break this down for us. So I equals 1/12 base times height cubed. And those are these things here. So the base times the height cubed. And for this, the base, B, equals 3.5 inches. We put 3.5 inches for here, 0.75 inches in here, 1/2. So we actually have this equation. We know what I is. So let's fill that in. So 1/2 B, 3.5 times H, which is 0.75 cubed. Fill all those in, and if you want to check me on your calculator, you can. but I'm going to give us the given that I is equal to 0.123, and our units are inches to the fourth. Inches to the fourth, because we have inches cubed here times inches is inches to the fourth. So we actually have a 0 here. I didn't round. It's actually out to 4 places with a 0. So that's our I. So we can fill in, now back to this equation, we fill in our I, we can fill in our H and our 2, but what about our U? Now the U, the ultimate strength for this wood, the ultimate strength of this wood is going to have to be looked up by the type of wood it is. Not all wood has the same ultimate strengths. So the wood we are using is called SPF, spruce, pine, fir. And for this, you can look up the ultimate strength, which I did for a 1x4. Our ultimate strength is going to be, so I'll just take this PSI part out. Ultimate strength for a 1x4 of length 18 inches is 7,300 pounds per square inch. So we've got that number. We've got our I. Now we can work back to our M. And the ultimate thing we're looking for right now is this force. What force does it take on that moment to break the wood?
Now, when we're talking about ultimate strength, that is when we've pushed the structure beyond its bending moment and actually break it completely through.
You write this statement over here, filling in for M what I have in the M equation. So I know that U is equal to, this is where I fill in M, 1/2 FL H, now I'm back into that, H, all over 2I. The only thing I don't know in this equation that I have not solved for is that F. So now I'm going to solve this equation for the F, moving everything around. This is basic algebra. If it has to move to the other side of the equation, it goes into the denominator. If it's already in the denominator, it moves to the numerator. So let's see, I want to start with F on its own side by himself. So if F is on one side, the U is on the other side. So we've got the U. We want to move the 2I over. We're going to go on top and everything else on the bottom. 1/2 LH. I can fill in all my givens. U, 7,300 times 2 times I, 0.1230, all over 1/2 L, 18, and H, 0.75. Run this through a calculator, and you're going to come up with 266 pounds. Now, if you're not very good with units, you can do a unit analysis of this equation so you know that you're coming up with the right equation, and it's a way to check your work. So the 7,300 was in pounds per square inch. The 2 is just a multiplier. The I had inches cubed, inches to the fourth. 1/2 was just a multiplier. L, which is 18, I had a unit of inches, so we got another inches. And 0.75 is also another inches. So maybe if I use some parentheses here, it'll be a little easier to see. But I have inches to the fourth on top, and then I also have inches to the fourth on bottom. Inches squared, inches, inches. So those all will cancel out, and I'm left with just pounds, lbs. 266 pounds is what it would take to break that 18-inch span of 1x4. But we don't just have an 18-inch span of 1x4. We actually have two 18-inch spans of 1x4. So I'll bring you back to this picture of the dolly, and if you remember, a ground view of that dolly was pieces of wood here, connected across, two pieces of wood there. And these are the pieces of wood that we loaded. These are our center of masses and our bending moments right here. Two beams in a dolly. So we take that 266, multiply it times 2, and we get 532 pounds on the two beams of the dolly. But it's rated for 1,000 pounds. So store dolly rated for 1,000 pounds. But the two beams of the dolly, now that we've broken it down, is only rated for half that. We didn't actually load one dolly. We loaded 3 dollies with a span of planks. Let me illustrate this for you. So we had 3 dollies, draw them this way, all connected with a span of planks across them as such. This was the load. The load was distributed across these 3 dollies. Now, how much load did we have? Now remember, the span that is stretched was in between the channel of the dollies, such that each of this, let me draw a front view. This is the side. Let me draw you the front. On that dolly, which had its pieces up here, its casters, all into the middle of those dollies, onto the 2 pieces of wood that can only hold 532 pounds. How much did we put on each of these casters? So let's come up with what the load was all together, and then we'll break it up into 3 parts. So the load altogether was 16 feet worth of wood. And the wood was 1x8 pieces of spruce pine fir. So that was 16 feet times 1 inch times 8 inches of SPF, spruce pine fir. We had 68 pieces. 68 pieces going across it. Now, how much does that weigh? So, what I looked up was the specifications of SPF for each of these, and I came up that each 16-foot length of 1x8 was going to equal 22.4 pounds. So that's what we get. 1,523.2 pounds, dry. Now we know for a fact that these planks were wet. We were bringing them from the paint shop area back to the main shop area on dollies, and they had just been painted and they were saturated. So I'm going to give them a 10% increase in their weight due to the water. And water is a very heavy substance, so this is generous. So we're going to give it a 10% increase for being wet. Means that you add 10% of that number back onto itself, and we end up with a weight of 1,675 pounds, rounded roughly, across all 3 of these dollies. So we split that into 3. This across all 3 dollies, let's say that, across 3 dollies, you take that number, 1675, divided by 3, and you're going to get about 558 pounds on each dolly. 558 is pretty close to what we had at 532, which means that, yes, we were definitely coming close to breaking those pieces of wood just by sitting the planks on top in an incorrect manner. Now, there's one more part of this situation that increased the load on this center dolly right here, which put the entire weight of the load on that one point, on that middle dolly. So what we had done is we took this loaded scenery on the 3 dollies and we brought it from the paint shop to the wood shop to be built. And we had to go up a ramp. Now the ramp was 22.5 degrees up. And a ramp starts out straight, goes up, and straight again. This is an exaggeration of it, but I need to exaggerate it in order to show you how we completely underestimated our motion. Starting out up the ramp, I'm going to use this as my load here. Let me turn it this way. We're going to pretend this is the loaded scenery. It's coming along, and now we've got to go up our ramp. And as you can see, the center dolly would be off the ground at this point in order to go up the ramp. We get up the ramp, and then what happens at the top of the ramp is that all of the weight of this load is on that center point of the pinnacle as it comes over the top to straighten out. But until it lands for a brief moment in time, and that's all it takes, all the weight was on that center dolly before it going over. And that's where we failed. This part right here is where our center dolly failed us. And of course it would. Why wouldn't it, right? We've got our scenic load here, casters off the ground here and here, and only that poor defenseless dolly right in the middle taking all of that load. And how big was that load? 1,675 pounds. 1,675 pounds. Now the dolly can take 1,000 pounds. Remember, a store-bought dolly could take about 1,000 pounds, but we didn't load it correctly for a store-bought dolly. We loaded it incorrectly onto just the 1x4 beams. Breaking the dolly was not inevitable. Breaking the dolly was a combination of mistakes, a combination of bad choices that led to overloading the dolly. How could we go about this without breaking it? Well, if we had simply loaded the weight properly across the casters, we'd be able to give 1,000 pounds to each, and 1,000 pounds to each, even going up the ramp, would put this at about 1,000 pounds. Also, if they were wet, and we knew they were wet, we should not have loaded them in the same way that we brought them to the paint shop. So we brought them to the paint shop dry, 68 pieces, and then we bring them back to the wood shop wet, increasing the load in itself. Thank you for joining me here at the chalkboard to talk about weight distribution loads on dollies. Next time when you're in your structural engineering class thinking about how to hang bridles and build trusses, you'll remember that not all the math and physics happens on the stage. A lot of it happens on the way to the stage. Hi, I'm Rita Roy, and I love math.
I hope you enjoyed this episode of Physics for Show. Next time people tell you that you don't need to know math for theater, you tell them where there's physics, there's math. And I hope you leave some messages in the comments about your experience using dollies.